Well, today I'd like to talk about folded cascode amplifiers. We talked about that a little bit last time. And then I'd like to talk about transconductance amplifiers, or what we call OTAs, which are in the current mirror op amp category. So again, where we're at, we're still on single stage now, high gain op amps. We'll spend another lecture or two on these, and then we'll move into two-stage op amps. Review of the last lecture. We looked at a regulated cascode amplifier. I realized we hadn't talked about that previously, but it's a simple structure with two transistors and an amplifier, and it has the property that the output impedance is very high. And if you bias it by a current source, it in and of itself makes a high gain simple amplifier. And then we use that to build an op amp. And the op amp we ended up with was this structure here. This is a gain boosted or regulated cascode telescopic op amp. And again, we wrote down the small signal characteristics of the structure by inspection. Then we asked if there are other things we could do to either increase GM or decrease the output impedance. And we came up with another structure, and another structure we looked at was actually just the cascode structure we had previously, except we replaced one of the N-channel transistor with a P-channel transistor. And we call that structure the folded cascode amplifier. When we first looked at it, it had a problem before we put this bias current source on. And what was the problem? Currents are flowing the wrong way. You can't hook them together. But we solved that problem by putting a second bias current in here, and then we could have a net current flowing in this direction here for this device, and a net current flowing in this direction here for the device on top. It has one interesting property that I neglected to point out last time. If you look at the signal swing of the cascode amplifier, where this is an N-channel device, we're limited to a VD-SAT drop here and a VD-SAT drop here. So we have two VD-SAT drops between here and ground. The cute thing about this structure is this has a VD-SAT drop here, plus to minus. It has a VD-SAT drop plus to minus this way here. If those two VD-SAT drops were the same, what would be the net voltage drop between the output node and ground? Zero. So what appears to be an interesting property of the circuit is maybe the ability to get additional signal swing. Make sense? If you analyze this folded cascode amplifier structure, and you include the non-ideal characteristics of M5, which we're using to bias that internal node, you can write some currents at that internal node, and you can find that the gain looks like this, simple analysis. I'm summing currents at two nodes. I don't have CL on here on the schematic. I'm assuming there's a CL on that output node, and then I have some currents at that node. So I calculate the voltage gain, and this is the voltage gain I get. GM1 over SCL plus Gout1 plus Gout5 times Gout3 over GM3. I don't feel so guilty about doing this analysis, because there's only two equations we had to write, and they're easy to solve. But let's see if we can write this down by inspection. So if you look what the cascode structure does, whether it's an N-channel or a P-channel, remember what the cascode structure does is it increases the output impedance. So it takes if you look at the output impedance you see in here, you started out with an output impedance here. if you ground this source from a small signal viewpoint, what you'll see is G out 1 from here to ground. It's one port. So when you create the cascode structure, you can think of replacing what's below it by G out 1. And then G out that you see here, G out equivalent, is equal to the conductance you see down here times G out over Gm of the cascode transistor. So we take the conductance we see down here and we multiply that by G out 2 over Gm2. Is that clear? The cascoding multiplies that conductance by G out 2 over Gm2. And the transconductance doesn't change. If you neglect the output impedance, you have GMV in here, and that is exactly the current that goes through this device. So the GM stays the same with the cascode structure, but the output conductance gets multiplied by G out over GM of that cascoding device. Now, if you look at the circuit here, if you look at the grounding the inputs, this is grounded and that's grounded. So M1 and M5 appear parallel. So the conductance we see to ground is G out 1 plus G out 5. So are you with me? The conductance we see to ground on this node here is G out 1 plus G out 5. And that will get cascoded or decreased by G out over Gm of the cascoding transistor. And that's what we see. G out 1 plus G out 5 is what we started with from that node to ground. And that gets multiplied by G out over Gm. Does that make sense? So what would happen if we put another transistor in there, connect to another DC voltage source? It would just add another conductance in that sum, right? Yeah. Okay. So we could have almost written down this expression by inspection rather than solving these two equations and two unknowns. Well, we now have then, I can write the gain expression for that structure, GM1 over SCL plus G out 1 plus G out 5 times G out 3 over GM3. And we can read off the gain right here, this over this. And the bandwidth is this over CL. The output impedance cancels. And the gain bandwidth product is GM over CL, which we saw before. So I'm adding to our table of characteristics now for the different quarter circuits that we looked at. We looked at the common source amplifier, the cascode, the regulated cascode, and now the folded cascode. And we see that the folded cascode doesn't quite give us as much gain, at least from a small signal viewpoint, as the cascode did. And why didn't it give us quite as much gain? We folded it, but what did that folding do to us?
Decrease the output.
It decreased the output impedance, and that means increase the output conductance. So it added this term in the denominator right here. So for the regular cascode, this term was 0. With the folded cascode, we have this in here. These may be comparable in size. So we might be suffering a factor of 2 reduction in the gain with this folded cascode circuit. Rats. And we didn't gain anything or lose anything, it appears, from a gain bandwidth product viewpoint. But we lost a little bit of gain. But what did we maybe benefit from? What? Signal swing. Our signal swing might be a little bit better on this structure. Okay? If we go into the practical parameter domain, I can express it like this. And now I'm letting theta be the fraction of the current of M5, that's an M1. So M1 and M5 don't necessarily have to have the same current, and that fraction of the current of M5 that is in M1 is theta, and actually we see now that the gain bandwidth product does get a little bit worse as well, because some of the power is being consumed in that biasing transistor M5. Does it make sense? So even though the small signal gain expression, the small signal gain bandwidth expression looked the same, when we went back to practical parameter domain, we saw we lost a little bit in GB as well. Make sense? Does this kind of show why it's important to go back to practical parameter domain? In the small signal parameter domain, we got fooled because it looked like they had the same gain bandwidth product. They had the same gain bandwidth product expressions. But if you look at the resource you have available, your excess biases and power, it's not quite as good. Does that mean we should discard it? Not necessarily. Signal swing is important in some cases. Here's the counterpart circuit. We can draw counterpart circuits in our sleep now, right? Replace N with P's, P's with N's, and we have a N-channel device biasing now instead of P-channel device. And now what can I do if I want to make an op-amp? Add them all together, right? And we get this. So this is a folded cascode op-amp. Now, if you go into your textbook and look at folded cascode op-amp, it doesn't look like this. This has 12 transistors, plus the transistor to bias the tail. The one in your textbook has 10. So that's one difference. And it wasn't drawn this way either. And that's another difference. Well, that's a difference in perception. It's not a difference in the circuit. So let's try to make this look like the folded cascode amplifier that you find in your textbook. If I take these transistors right here, these 4 transistors, this one has its source connected to VSS and its drain connected to VDD. Okay? That's weird. So one of the transistors down here has its source connected to clear up here. So I could redraw this circuit if I wanted to. Like, oh, by the way, there's a second loop that does the same thing. The right-hand side, you see the similar loop. VDD through these 4 transistors back to VSS. So I could just redraw the circuit. And if I redraw the circuit, I get something like this. Now this is close to the circuit that you see in your textbook. But this circuit still has 12 transistors. So what I've done is I've taken M1 and M2 and I just pulled them off the side here. It really looks like a different circuit, doesn't it? But all I've done is redrawn it. And then I picked M11 and M12 and pulled them off the side and did the same thing. Now, if I look at M11, M12, M7, and M8, let's see what functions these are performing. What is M7 doing for us? It's serving as what?
Active mode. Put it in there.
Actually, it's a current source. Put a fixed gate voltage on that causes a current to flow here, right?
Yes.
So M7 is serving as a current source. And how about M11? What's it serving as? It's what? Another current source. So M11 and M7 are serving as current sources. One current source is providing a current coming in and one current coming out. And the net current coming this way is going to have to be positive. So we've got two currents that are adding together in opposite directions to result in a net positive current. Why do we need two current sources to make one sinking current? So if I wanted to, I could say, let me eliminate M11 and just resize M7 so it has the current coming out of the tail of M9. Make sense? So these transistors pairwise form a current source, and one can be removed. The same comment refers to M8 and M12. Okay? So if I remove those extra transistors, then I end up with a structure here. And this was shown in your textbook. Okay, again, we synthesized it. And we've looked at the equivalence of two current sources to end up with a structure here. This still needs a common feedback circuit for VB4. We can have either single or differential outputs. That's inherent on any structure that we form starting with a quarter circuit. We can connect the counterpart circuit as a current mirror to eliminate the common feedback circuit. Folding of the structure here causes a modest deterioration in AV. We saw that because it happened in the folded cascode configuration. And a modest deterioration in GB efficiency because of what? We had some extra current that we had to bias that cascode, that folded cascode device. But it has the benefit of a modest improvement in output signal swing. So we know that any of these structures have a voltage gain that's of this form, where AV0 is equal to GMEQ over G out equal Q, and where GB is equal to GMEQ over CL. So, do we want to analyze this circuit? Now I go back to MATLAB and analyze this circuit. I did it for the telescopic cascode. This has more devices in it. So I don't think I want to do it. I don't think I want to do an analytical derivation of the gain character of this structure. Make sense? But I'd like to do it by inspection. And we're almost there. So, how does GM of the folded cascode block relate to GM1 of the input transistor? They're the same. So GM equivalent is going to be GM of that cascode block, which is going to be GM1. Okay? So I've got that. Now, G out equivalent. Oh. So let me assume, I've actually got, I really didn't want this in here yet. This is a current mirror connection. Let me leave this out. I don't need both the bias voltage and this current mirror connection. Let me leave this out right now. So let's see if we can get this by inspection as well. The output conductance is the output conductance we see on this node. And the output conductance we saw on this node was the G of this structure plus G of this structure. The output conductance was the two G's. So let's get those two conductances. If I look down here, this is a cascoded, this cascodes the conductance of this. So the conductance I see down here will be G out 8 times G out 10 over GM10. Is that clear? The conductance I see looking down here is G out 8 times G out 10 over GM10. The conductance I'm looking at here is G out 4 over GM4 times the conductance I see on this node. And that's G out 6 plus G out 1. Is everybody with me? Now, I've looked on the right side, and so let's write that down. So we have G out EQ is equal to G1 plus G2. And we saw G1 was G out 8 times G out 10 over GM10. And then we saw that G2, the one on top, was G out 4 over GM4 times the conductance we saw on here, which was G out 6 plus G out 2. Is that clear? No, that's not what I've written here. But if the left and right side are symmetric, then I can replace G out 6 by G out 5, I can replace G out 4 by G out 3, and so forth. And that's what I have written here. So what do we have? We've got G out equivalent, we've got GM equivalent, and as I've got the gain, as I have here's the gain expression, the DC gain, I have the gain bandwidth product. Any questions? If I did a MATLAB analysis, I might have had 10,000 terms in that transfer function. How many are left once I write it in this form? About 4 terms. Of that 10,000 terms, there's about 4 terms that are left. There will be big, long expressions. Most of them are small compared to the others, and then a bunch of stuff will cancel. So I could go through that 10,000 terms, find out the 4 that are dominant, and then make the cancellations take place, and I'll get this. Do you think that's fun to do? It's not too hard. Once we have those 10,000 terms, MATLAB has tools that allows you to scan through that set quite quickly and find out which terms might be dominant, but it's not completely tedious. You don't want to miss one. So now I can compare the operational amplifier structures in a small signal parameter domain. I've got the reference op amp, the telescopic cascode, the regulated cascode, and the folded cascode. These are all for single-ended outputs. And I've got the slew rates. Of course, the performance of these structures is really determined not by the small signal parameter domain, but by the practical parameter domain. So here's the corresponding expressions in the practical parameter domain. And we see that decrease in GB efficiency in both the regulated cascode and the folded cascode. In the regulated cascode, because we have power that has to bias the amplifiers. And in the folded cascode, we have to bias that cascode transistor. Okay? How many degrees of freedom do we have in this structure? And what's the practical design parameter set? Well, if you look at the structure, it's got a lot of degrees of freedom. I tail, W1 over L1, W5 over L5, W3 over M3, W9 over M9, W7 over M7, and the bias voltage is dB1, dB2, and dB3. So we have 9 degrees of freedom in this design.
practical design parameters, well, we can pick different sets, but these work pretty good. The power, total power, theta, the amount of the power that you spend in peripheral circuitry, and then your excess biases. Of course, the number of practical parameters I have is equal to the number of degrees of freedom I have in the design. If you want to look at a different view on the regulated cascode, the folded cascode, the telescopic cascode amplifiers, they're in Chapter 3 and Chapter 5 of your textbook. Oh, what's this? Miss Alva.
So it's the same as like the other gain boosted.
Same as the other gain boosted, we can do gain boosted on the folded cascode as well.
You kind of like combined both the regulated and the folded, it looks like.
Yep, that's right. So we're combining folding and regulation on here. And of course, the gain's going to go up by a factor of A. So modest improvement in this output signal swing of the structure like we had before. This is with an ideal current source bias. With a practical bias, we have to put that biasing transistor in. I'm just going to step through these quickly. We can again write all these expressions down by inspection. And so now we've added the folded regulated cascode to our basic amplifier set. Its properties in the small signal parameter domain. Its properties in the practical parameter domain. Here's what the folded gain boosted telescopic cascode op amp looks like. No big surprises, just have those four. Now we got two penalties here. Power two places. Power to the A amplifiers and power to biasing that folded device. Still, we need a common feedback circuit if we want differential outputs, but we can connect the counterpart circuit as a current mirror to limit the common feedback circuit. The folding caused a moderate deterioration in GB efficiency and gain, and the gain boosting did it as well. But this structure has a modest improvement in signal swing. If you look at the number of VDSAT drops between VDD and VSS here, what do we have? Actually, it's 4. We've drawn it a different way. So this is P, VDSAT, 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 VDSAT. So we have 4 here. Or we go this route. We have 1, 2, 3. So it looks like that we have at least 4 VDSAT drops between VDD and ground, compared to 5 VDSAT drops, or 5 VDSAT drops plus a VT if we have a current mirror connected structure. So I've added now the folded regulated cascode characteristics to our table in the small signal domain. And I guess I don't have a table here that shows it in the practical parameter domain, but it's easy to write down. I should point out there are a lot of papers that uses the folded cascode op amp. I think a few of them use it for the right reason because they get a little more signal swing. I think another reason a lot of them use it is it's been kind of a catchy name and a catchy structure as well. But it's reported in a lot of papers, and a lot of people in the industry use the folded cascode op amp. The gain boosting, whether you do it on the folded structure or on the non-folded structure, I don't see near as much use of that. Fair amount of additional effort to put in those gain boosting stages, and oftentimes we don't need that higher DC gain that we get. Yes?
So I have a general question about all of these structures. Aren't we kind of missing some of the picture when we talk about slew rate and bandwidth, because we're not accounting for the internal capacitance of the quarter circuit? Or is it not significant enough to where?
That's a good question. Well, we haven't talked about compensation yet,
Yeah.
but we don't have to compensate single stage structures. Now, really, these Cascodes are two stage. We have a common source driving a common gate stage. But what we find is the impedance on that internal node is so low that the extra pole that we introduce because of the capacity of that node is such high frequency it can usually be neglected.
Oh, okay. So it is,
So it is there, we've neglected it.
but we can, it's okay because.
It's okay so far.
Because when-
Now, once you put those A amplifiers in, now we've added another pole in that A amplifier. So we're neglecting two poles. We're neglecting the pole on that Cascode node, and we're neglecting the pole on that A amplifier. The argument is we're going to use a high-speed, low-gain amplifier for that A amplifier. So hopefully it also has a high-frequency pole. So hopefully we can neglect that pole as well.
That makes sense.
Okay? But that's a good question. It says there's two more poles. Sometimes we have to at least check and see what effect those two additional poles might have on the phase margin of our amplifier. Yes?
It's generally because, like, on two-stage amps, right, the second stage is, those transistors are so much bigger that the capacitance moves that pole in, right? And that's why you need the compensation, right? On like a single-stage amp, the transistors are sized generally small enough that that's not a concern, that the poles are way out.
Yeah, that's right. We're going to show shortly that you have to have a major separation between the dominant pole and the next pole. If Mr. Kimmler hadn't interrupted the process here, I would have glossed over the fact that there's a couple more poles in the Cascode and the folded Cascode that are way away and we just don't have to worry about them. But he is correct. They are there, but they're usually far enough out that they don't cause a problem. When we get to the two-stage structures, we're going to find that they're not very far out, and we definitely have to worry about it. After we get back and study how to handle those pole locations of the two-stage structure, then if we want to, we can come back and see if there was an issue on the folded Cascode and the regulated Cascodes. Make sense? So I'm glad you brought it up. I was planning on hiding it until we got down past the two-stage amplifiers. Well, let's go look at this gain expression again. And the Cascode, the regulated Cascode, the folded Cascode are all focused on decreasing the output conductance to increase the gain. Let's ask the question, can we increase the GM in the numerator to increase the gain? Because that's another way to get a higher gain amplifier. So let's now consider increasing the numerator. We'll look at a couple of different ways to do that. If you look at these structures that we synthesized, we really looked at the counterpart circuit as a current mirror. So we could use counterpart circuits from other structures as well as that current mirror on top. Now, for the most part, you're going to show that if you have a cascoded quarter circuit and you use the current mirror off of a single transistor counterpart circuit, you're going to find that you'll get a fairly significant degradation in performance because the output impedance of that other quarter circuit is too low. So we like to use the counterpart circuit of the quarter circuit, but we could use other counterpart circuits. But we could just think of putting arbitrary current mirrors on top as well. Different current mirrors have different characteristics. By the way, we might be able to take some of the different current mirrors that we've talked about and go back and extract from those a quarter circuit and maybe come up with some different op amps that people haven't looked at. So, I made a comment that looking at this approach, we might be able to actually come up with different structures. Okay? So let me now think of just putting current sources on top there. And if I put current source on the top, I don't suffer from the G2 term that's on top here. And my gain goes up. V out minus over Vn is equal to minus GM1 over 2 times SCL plus G1 plus G1 of the biasing current source. Well, this is the same expression we had before, I guess. This was G2. I just used G of the biasing current source down here. So what if I took and put a current mirror on? And the reasoning goes something like this. When we create the differential structure, we talked about the current that came down the right side from minus VV over 2, and then the current that got mirrored around, and those two added together. What if we took a transistor and went straight into a current mirror and drove that to the output? Dominantly, the current here, if you neglect the output conductance, is GM of this transistor. And that signal current is going to get multiplied by the mirror gain. So the signal current we're going to steer to the output load is now going to be the mirror gain times GM1. If we use a single transistor or quarter circuit, the current we steered to the load was just GM1 VN. This will be GM1 VN times the mirror gain. And it's real easy to make a mirror gain of 10. If we make a mirror gain of 10, we're going to be steering 10 times as much current to the load. If we steer 10 times as much current to the load as proportional to Vn, we should increase our gain by what? By the mirror gain of the current mirror. Is that pretty clever? So GM equivalent of this, if we use this as a quarter circuit, GM of this is going to be GM1 times M. So GM is increased by the mirror gain. So see what we're doing? Instead of attacking the denominator, we're attacking the numerator, trying to make the numerator bigger. We may have to fold this structure to get the right bias current configurations, but we know how to fold a structure now. So I'm going to consider using this quarter circuit to form an op amp. I could have done this with other quarter circuits as well, but right now I'm going to look at this structure here. And there's some output impedance to this circuit. That's the output impedance of the quarter circuit. So if I look at the GM of this quarter circuit now, it's GM1 times the mirror gain, and G out of this quarter circuit is the G out we see looking into this, plus the output conductance of whatever bias current source we're going to put on the output. If I fold that current mirror, take currents going in the right direction, this is the structure I end up with. This is my whole op amp. So here's my bias and current sources. The current here is mirrored to this location here and steered to the load. Is that clear? So what we're doing is we're taking two quarter circuits and bias current sources of IB to form our op amp. And this is called a current mirror op amp. It's a very simple structure. The premise is the transconductance gain has been increased by the mirror gain. It has. So GM equivalent is going to be M times GM1 over 2. The GM1 over 2 because we're putting differential excitations in. If the output conductance is small, then the gain can be very high. The GB is very good in structure as well, it appears. We still need to generate the bias current. Let's not worry about that right now. Here's my current mirror op amp. I mirror these currents to the output, and here's the biasing current sources. Biasing current source here and a biasing current source here. These two IVs, bias and tail current. This structure still needs a combo feedback circuit to establish just a minute now. To establish the voltage here on VB2. And if I want to, I can replace those current mirrors on top here with higher output impedance current mirrors. We talked about more advanced current mirrors that could go in there. And I can eliminate one of the outputs and do current mirror biasing on the biasing circuits, just like I did with the other structures, and that eliminates the need for the combo feedback circuit. So the question is this a real clever solution? Just using current mirrors to increase the transconductance gain of that MOS transistor. GM equivalent we saw was the mirror gain times GM1 over 2. The output conductance on this node or the other node is the conductance we see looking here plus the conductance we see looking here. This conductance will be G out 8 and this will be G out 6. So the output conductance is G out 6 plus G out 8. The GB is what? Well, I have to find the bandwidth, and that's G out 6 plus G out 8 over CL. The gain is the ratio of this. This cancels, so the gain bandwidth product is the mirror gain times GM1 over 2CL. What do we have for the gain bandwidth product for using a common source amplifier as a quarter circuit? GM1 over 2CL. Ah! So the gain bandwidth product has gone up by the mirror gain. The voltage gain, compared to the single transistor quarter circuit, we had this for the voltage gain. It's been increased by M. The slew rate was I tail over 2CL before. It's been increased by M.
What about the power consumption?
What?
What about the power consumption?
Oh, didn't look at that yet. You're really making a rainy day for me. Okay. So, in the small signal parameter domain, it appears that we've got a dramatic improvement in performance of the structure. We've increased the gain by M. We've increased the slew rate by M. We've increased the gain bandwidth product by M. And it's real easy to make a current mirror with a large M. Is everybody convinced? Ignore his comment. Ignore his comment. Is everybody convinced that we've got a big improvement? At least in the small signal parameter domain, it appears that's the case, right? This is called the current mirror op amp. It's a very simple structure. And it's a clever solution. There was a paper published in 1969 or something by Wheatley and Whitler, the people that coined the term current mirror, and they say the OTA obsoletes the op amp. They were predicting that this structure was going to do away with the conventional op amp. Well, it's pretty nice because there's not many transistors in it. You have a differential pair and a current mirror, you're done. Make sense? Real simple structure. Here was the original structure. You can show it's essentially equivalent to what I've talked about. Let's not worry about those details. What did you say? What about the power? So next time, if the sun's shining, we'll come back and talk about the power dissipation. That's all for today. Thanks.
Great. That was great.